Good afternoon. I'm actually really excited to see so many people in an indexing session. I've had multiple people come up to me and tell me, I can't believe you have 2 whole sessions on indexes. And it makes me laugh and smile because when I teach performance tuning classes, I actually have 2 full days on nothing but indexes. Now, I'm not intending to make everyone in here kind of an index internals guru to know every little thing about indexes, because that's not always what's necessary. But in terms of performance tuning, indexes are one of the most effective ways of tuning performance with the least impact to application development and design. There is nothing, absolutely nothing in SQL Server that will give you as good of performance gains with as little work as indexes are going to. I've looked at queries that take 5 minutes, 6 minutes to run, just to give a really good example that I'm thinking of. And literally, well, I'll start with, I made this fatal mistake of saying, sure, I'll take a quick look at that. And it turned out to be a 27 table join with 13 left outer joins. And I remember going, okay, this show plan isn't the most simplistic show plan I could have looked at. And literally, I looked at it, I started analyzing some of the join types, and I even look back on this and say, the fact that I knew how SQL Server internally processed joins hurt me in tuning this, because I looked at the join type that was expensive out of this big, fairly complex plan, because there was one of the joins that was more expensive than others, and I went, ooh, it's doing a loop join, so I need this type of index. Again, using all the internals that I know about indexes, and I brought the query down to 2.5 minutes, which from I think it was 5 minutes, 19 seconds, down to 2.5 minutes is a good improvement. However, if I had not known necessarily about the right type of index for the loop join, if I had instead taken some kind of generic best practices for indexes and said, well, it could be one of these 2 different types of indexes, and I put both of them into place to just let SQL Server tell me which is the one that is more effective and more efficient, I would have found out even sooner that the index that I didn't think of first brought the query down from 5 minutes and 19 seconds to 2 seconds. And there's absolutely nowhere in SQL Server that you can get those types of gains with a very simple design change. And in fact, if you change design, in some cases, you may have to change all of the code that accesses those objects. I make the comment, the sooner you begin to code, the longer it's going to take. If your schema is not stable and you start coding to a schema that ends up changing, then you end up having to recode those objects. So when I start looking at all of the different options that exist in terms of performance tuning, one of the easiest things to do, which does not require application change, is to create the right types of indexes, to structure your tables appropriately so that right from the start, based on what you think, and that may not always be true, but what you think are going to be the uses of those tables, you can, through some best practices, set up to get better performance right from the start. And that's really the goal of this, is how can you, with some best practices, some basic concepts in internals of tables, table structures, usage of those tables, how do you end up getting a base table structure that is just more proactively performant? So this is really the first of 2 sessions. This one is on the best practices in terms of creation. And I do want to stress something. It is kind of a 2-parter, only in that if you don't maintain those indexes, they are going to start to degrade in their benefit over time, and they're not going to be as effective and as efficient. So it is very important that you also consider index defragmentation best practices if you have inserts, updates, and deletes. So let's talk a little bit about what we're going to cover here. My name is Kimberly Tripp, and I've been working with SQL Server forever, it feels like. For the last 10 years, I've been independent of Microsoft, doing training, consulting, speaking at different conferences, seeing and tackling various customer problems, usually related to performance tuning and availability, working on a lot of different resources. A lot of the links are from my website, and I always do this, but I will post not only all of the scripts for the DVDs so that you guys have those there, but I also post all the demo scripts on my website so you can reproduce everything that I demo here. So really the most important thing from this slide is just to go to SQL Skills so you can download these scripts. And, kind of interesting, about 75% of what I demo here, most of you can get away with working on not only SQL 2005, but SQL 2000 as well. So really, the best practices in general between the different SQL versions have been very similar since 7.0. 7.0, 2000, 2005. But again, I don't always see them being followed. So that's what we're going to talk about. The first thing we have to talk about, though, before I can cover indexes, is talking a little bit about whether or not your queries are going to use those indexes. Because as much time as you take to create indexes, you have to make sure that your queries are efficient and more effectively using those indexes. And there's some very simple, basic practices to follow that will make your queries more likely to use indexes. So we're going to start with that. Then we're going to talk about the concepts and internals of indexes. The reason I do this is I want to make sure that the physical structures kind of are in your head a little bit as I start talking about index traversal. I'm going to talk about leaf scans. I'm going to talk about seeks. And I'm going to talk about how indexes are used. And by having visualized those indexes, you're going to end up being able to even calculate, if you desire, the number of IOs that it costs to process your queries. You can literally say, oh, well, if they're going to do an index seek with a partial scan, that's going to cost 1, 2, 3, and X number of IOs. And by visualizing the structures as I show you the right index types, you'll start saying, okay, I visually see how that's going to be used. So concepts, internals, then we'll talk about my general recommendations for the clustering key, and then how non-clustered indexes should be used effectively. Because, and this is very counterintuitive, you will often get better performance with non-clustered indexes for range queries than you will, in many cases, the clustered index. In fact, I'm going to throw something out here that I'm going to kind of dangle as this principle that by the end of this session will be really clear. But in SQL Server, it's generally better to have fewer wider indexes meaning multi-column or composite indexes. Generally speaking, it is better to have fewer, so less indexes, that are wider than it is to have lots and lots of narrow indexes. In fact, the usefulness of a narrow index, meaning let's say just one column, is actually quite low. In fact, if your query returns more than roughly 1% of your data set, that query is not likely to be selective enough to warrant the use of a non-clustered index, which is an intriguing principle. A query that returns more than 1% of data is not selective enough in most cases to use non-clustered indexes for those ranges. So if any of you guys are writing queries that return more than 1% of your data, right, you need to get some insight into how non-clustered indexes can help to aid in the performance of that particular query. And there are certain things you have to do to your queries to make it more likely to be used. So pros and cons of non-clusters, where non-clusters are really effective and useful. And then I get this question a lot. I've seen people give me schemas, and they say, how do I index this? You know, they always want the one right answer. And with non-clustered indexes, I'll tell you that you actually have levels of improvement that you can get. You can say, well, if this is a really critical query, I might go for this strategy. But if it's not quite that critical, then I might be able to leverage this other strategy. So what I'm going to do with aggregations is I'm going to show 4 different levels of improvement that you could selectively choose to implement based on the priority and importance of your queries. So what I'll be able to do is give you some really solid demos that will help you start to gauge when and what type of tuning you should perform. So we'll round out the session with how to keep performance optimal, but just briefly, because that's when I'll move into the next session and go into index maintenance. So starting out with the usage of indexes and the conceptual usage of indexes. Most people know this. It's, you know, why does SQL Server use indexes? Generally to speed lookups. And most people think that only applies to selects. But that applies to anything that has a where clause, for that matter. If we're going to update a row, it's important to know where that row is, right? And indexes can help us find a row for a query, for an update, for a delete very quickly. And also, what about an insert? Where does that row need to be inserted on an insert? Well, if there are indexes that help us direct the row to a specific location, then knowing where that row should be inserted is faster. So indexes help not just queries, but also inserts, updates, and deletes. So you really need to think a little bit about that. And then people tell me, well, why not just index everything? I actually went somewhere once and looked at a series of tables and kind of took a step back and said, wow, you guys have a lot of indexes. And they said, yeah, we have an indexing strategy. And I was, wow, okay, what's your strategy? We automatically index every column. And I'm like, okay. I've become politically correct, at least more so in the years. And I was like, I think we may need to evaluate this strategy this week. And again, that concept of lots of narrow indexes is that they aren't as effective as fewer indexes that are more strategically put in place that are wider indexes, meaning more than one column. So the index strategy concepts, fewer indexes are usually better than lots of indexes because they do have overhead, and the right types of indexes are what's really going to give you great gains. So how do we make sure that the indexes we create are going to be used? And the answer is write more effective queries. This is a very simple premise. I know a lot of us, myself included, select star from table. I do that a lot in a quick lookup. I never do that in code. Okay, I would never put that into a stored procedure. I would never necessarily put that into a view. Some people create views that are essentially a direct representative of all their tables. That's not so bad, but when you query against the views, it's a good idea to end up limiting the select list. If you can make your query a narrower projection, meaning a narrower limited set of columns, the optimizer has more options to optimize your queries. It may not be immediately obvious, but the narrower your query is, the more targeted your request, the more options the optimizer has for optimizing that request. So if you can limit the column list, that's the first step. But if you can also limit the row set to the smallest row set that's possible and try to give SQL Server a positive search argument, then it's very likely that you will use more and more effective, efficient indexes with a lot less IOs. So a selection, this is kind of an interesting one just to point this out. I see this all the time. You might have a column that is something like monthly salary, and then somebody wants to analyze based on an annual salary. So what a user, if a user has ad hoc access to the database, is very likely to write is, I want to find out all of the rows where the monthly salary times 12 is greater than some particular salary. But the problem with that is that when you have a column with some form of calculation, they're going to have to calculate that out for every single row, which is going to require some form of scan of the data. Not necessarily a table scan, but some form of scan of the data. And if they have to scan the data, they have to touch every single row, which is not as effective as when you can seek. A seek is where we have a limited select and we have some type of, usually, comparison to a constant. So if we can isolate the column to one side of the expression just by rewriting the query a little bit, you might be able to get some huge gains just in doing that, not even necessarily changing your indexes. But if you require scans, you're going to be less likely to use indexes. So by having seeks or focusing on more selective types of queries, you are more likely to use indexes. So I would strongly suggest things like views, stored procedures, functions, table-valued functions that return limited data sets to simplify the user's interface. So that if the user, out of, well, writing SQL isn't their everyday job. It's this secondary thing that they do when they have to get data. And as a result, their queries are not the most optimal and effectively written. So instead, if I create a view which does that 6-table join more efficiently and they select from the view, I can already and more proactively write the correct join and limit their column set. So again, stored procedures, views, functions are a good way of limiting that data. And then we get to indexes. So, all right. We've talked about being able to find data quickly, and this is a really simple concept, but I love this analogy because I'm going to use it again and again here just to reiterate how non-clustered indexes work. A book, literally, books that we read that we want to find out some details on, we often go to the index in the back of the book, and it tells us where the information we're interested in is within the book. And we are effectively doing what's called a bookmark lookup. right? We're going to the index, which is usually ordered. We find out the information that we're interested in, and we go into the data to find the exact information that we're looking for. You can have many indexes in a book. Most books don't, but if you think of a book on animals, you could have an index by scientific name, an index by common name, an index by continent or type of animal. I mean, you could think of all sorts of different ways that you could end up indexing this information. And what you would be storing in the index, if you think about it, is literally a subset of the information about that particular animal, right? You take literally the scientific names and you're duplicating them in a structure that is ordered in the back of a book with some form of reference to the data. This is exactly how SQL Server's non-clustered indexes work. I'm going to tell you how they physically work in a second, but conceptually, you go to this index which has some form of order to it, and it says where the information lives. So that's one concept. Now, the actual structure of an index follows this analogy. Very simple analogy in terms of a tree. If all of your data looked like a tree, like literally a tree outside, and you went out to that tree and you had to find all of the leaves, imagine the leaves are your data. You had to find all of the leaves that match some particular criteria. You could literally stand out there and touch every single leaf on that entire tree. And you would be effectively scanning that data, which isn't very effective. Now, if you were looking for some property where all of those leaves were grouped in one area of the tree, and we even knew, starting at the root, what the right direction was to get to that set of leaves, then you would access only the leaves that are necessary, and that would be a lot more effective. That is a seek. Every index type, no matter what type of index, clustered indexes, non-clustered indexes, even with the new include features that I'm going to talk about, every index is structured like a tree, and every index can do both seeks and scans. So now we have to start getting some insight into what the physical structures look like so that we can now create the right indexes. So the physical structures. The leaves of an index have data. Now don't get me wrong, it's not necessarily the data row. It's usually a subset of data, but that depends on the index type. So now let's get specific. There's two types of indexes inside of SQL Server. There are what we call clustered indexes, and then there are non-clustered indexes. A clustered index, what you're going to end up doing if you cluster your data, you will be physically ordering the data itself by your clustering key. So literally, the leaf level, the data of a clustered index is the table's data. So it's literally like taking your table of employees and saying, I want that data to be ordered by, let's say, employee ID. They will literally take your table. Let's say it's not ordered right now. Let's say it's a table that doesn't have a clustered index on it, so it's kind of randomly ordered. You're going to take that table literally when the clustered index is created and pick it up, copy it, and reorder it based on the clustering key. It's quite expensive to create a clustered index when one doesn't exist because your data does get duplicated. They will then order all that data by the clustering key. So what was unordered gets picked up, shuffled around, and now it's in order by, I think I said employee ID. So we'd have 1 through 20, 21 through 40, if let's say we fit 20 records per page. So literally all those pages would be ordered. That's the leaf level of a clustered index. Since the leaf level of the clustered index is the data, you can only have one per table. That's kind of the book. Then you can have secondary non-clustered indexes that have some reference into the data. Now, the table doesn't have to have a clustered index. You've never really been told that you had to have one. I'm going to strongly suggest that you do have one in most cases. And when you do, the way that the access from the non-clustered indexes into the data is by referencing the clustering key. So let's say you create an index on Social Security number, or some type of identifier that's not the employee ID. They will then take the Social Security number and the employee IDs, duplicate them into a structure that's ordered by Social Security number, and if we look up Social Security number 1, 2, 3, 4, 5, 6, 7, 8, 9, we'll go into that index, we know exactly where that is because they're ordered, and it will tell us what the employee ID is, so we go back to our index structure and we find that row. It's very, very efficient. So we'll start to look at some things that maybe aren't quite as efficient when we do that. But that's a bookmark lookup. Now, they do have a new feature in SQL 2005. Typically, what you've had the capability to do with a non-clustered index is define what the index is on, like social security number. Then they will automatically put the clustering key in there. But to keep the tree structure that helps us navigate this information as small as possible, they restrict the maximum size of the key to 900 bytes or 16 columns, whichever comes first. So what this means is that the maximum width of your index definition is 900 bytes or 16 columns. And when it turns out that I'm going to tell you that non-clustered indexes can be more helpful for range queries, you may, in some cases, want to have a wider structure to help support some of your queries. That's a feature that SQL Server 2005 supports. You can create an index where the data is ordered by an index key that is still limited to the 900 bytes or 16 columns, but you can add additional columns that are just in what we call the leaf level of that index. And as we see the physical structures, this will make more sense. So that's a new feature. Now, just another note on why that's so interesting is that the key, the tree structure, stays small and efficient. But the leaf level can be wider to allow more effective, what we call covering queries. Now, before some of you start going, oh, she's talking about covering? If you know that term, and maybe you think of it as negative, which is unfortunate, because I don't want you to cover every query, and that's often what people think is negative. She's just going to tell me to cover all 87 of my queries. That's not true, actually. It's exactly the opposite of what I'm going to tell you. I'm going to tell you that some covering is required, really, to get better performance. But what you need to do is prioritize, find the worst performing range queries, consider covering some of those, and through some of these secondary and internal algorithms that the optimizer uses to process your queries, you might have strategies that you wouldn't necessarily have expected for the other queries, giving them benefits as well. You don't need to cover everything. And I'm not even going to recommend you cover a large percentage. But if, let's say, you look at 10% of the worst performing, most important, right? Priority is important here. So the worst performing, highest priority queries, and you cover or consider covering for some of those, you'll probably solve 80 or 90% of your problem. It's quite amazing how effective these indexes become, even in ways that you don't expect. And I'm going to demo this, so you'll start seeing this in a moment. So covering indexes are very important, and what include gives us the ability to do is create more interesting covering indexes. Now, we will talk about index views as well. So let's get to the table structure. The table structure, as I mentioned, doesn't require a clustered index. So there's really two types of table structures inside a SQL Server. A table could be what we call a heap structure, which is a table that does not have a clustered index. It's called a heap. And then we could have a table that does have a clustered index, which is called a table that has a clustered index. You know, I wish there were some special term for it, but there isn't. So it's either a heap or a table that has a clustered index. For simplicity, I'm just going to call that a clustered table, but I don't mean to confuse that with any other product's term, clustered table. So it's either heap or it's a table that has a clustered index. Now, these next 2 points are really interesting. Non-clustered indexes, the existence of non-clustered indexes, does not in any way, shape, or form impact the base table structure. They're irrelevant. But the table being a clustered table or a heap significantly impacts the non-clustered index structures. So what you should immediately start thinking is, okay, my base table structure is what helps to define my non-clustered indexes, so I better choose wisely what my base structure is. Should I go with a heap or should I go with a clustered table? Now, there are some benefits to a heap structure, but generally speaking, they are not the most optimal. I probably could spend an hour on why heaps are bad choices, but because I really think that clustered indexes are good choices, I'm just going to hit a couple of highlights for heap structures. A heap is a collection of unordered pages with no doubly linked list associated with it. There is no order whatsoever to that data. So where does a row reside within a heap structure? I don't know, right? So how do we access data in a heap structure? Well, without indexes, we don't know uniqueness, We don't know order. We don't know that there really is only one record with a value of 1 on the first row on the first page, because without uniqueness, we don't have indexes, we don't know that it's unique, right? So complete and total scan would have to be performed. Now, you could have non-clustered indexes with a heap, but some of the negatives that you see with a heap are going to be in terms of scans when there's updates, right? And again, not getting into too much, there's a good knowledge base article actually on this, but the way that they track where the pages are is through a structure that really, I'm still using the term IAM because I really like saying IAM a little bit better than the HOBT, which is kind of what they're using in SQL 2005. But it's the same term, it's just or it's the same concept, it's a slightly different term. So an IAM is a map of where the structures live for a heap or a B tree. And a heap structure will have a map, so will an index. An index has a B tree structure, and that's what we're going to look at in a moment. So these IAMs, or these heap or B tree maps, are going to tell us where the pages are that a table lives on. So you might think if a table has 4,000 pages, that the number of IOs that it would cost to read that table would be 4,000. And that's what I would have thought as well. But because of some optimizations that they do for non-clustered indexes, it turns out that you might end up having something called forwarding pointers. And forwarding pointers do have a pro to them. And it has a lot to do with index manipulation. So I don't want to drone on that, but there are some pros. One of the cons, though, is if you have a lot of forwarded records, it costs you an extra I/O to go from a page that has a forwarded record to read the record to then go back to figure out what else you need to read. So a table that has 4,000 pages with, let's say, 1,000 only forwarded records is going to be 5,000 IOs. And the bigger and bigger the tables become, the less effective they are for large scans. So if your table has inserts, updates, deletes, singleton manipulation, and analysis, then a heap structure is not usually the most ideal choice. But there is a pro. If you've never done a delete or you've never done an update, there's a special case with a heap structure that effectively says you don't need to find where the row should be inserted because there are no gaps. We've never done any deletes. A heap is very space efficient, right? If you think of an unordered set of data and then a row gets deleted, a heap structure is going to reuse that space, which if you think about it, is going to help keep that table more compact. But that's at the negative of performance. But if there's never been a delete, if there's never been an update that caused a row to move, there won't be any gaps, so we don't, on an insert, need to find gaps. We can just end up throwing in pages at the end. That gives inserts into a heap much faster performance if you're going to do a large-scale load. So we tend to use this term if you're staging data in and you want to get more optimal performance, you can end up going ahead, creating a table with no indexes, loading that table, possibly even loading it from parallel files, right, bulk loaded files, and get parallelized bulk load, get the data in, and then you can end up creating indexes on it, which also can be parallelized, and then you'll end up getting significantly better performance than if they had to do the index manipulation while they were doing the load. So one of the greatest choices for really effective data loading and data warehouse builds is often to create an empty table, load into it, put your indexes on it, and then kind of put that object into usually a more complex partitioned type of object. In fact, I am going to talk more about partitioning in the VLDB strategy session tomorrow if you're really interested in kind of that concept of dealing with large tables in smaller, more granular chunks for performance. If you have a VLDB, it's a much more effective way of dealing with those large data sets. So if you're staging data, yes. But if it's a day-to-day table for inserts, updates, and deletes, I wouldn't consider a heap. So there are some pros, but not for a regular table. So just to stress again, you can parallelize the bulk load, you can parallelize the index creation, and if there's never been any deletes or forwarded records, heap scans are efficient, but as soon as you add inserts, updates, and deletes to the mix, heaps usually start to degrade over having an appropriately structured clustered table. Now, I smile on that because there are two types of tables, I've told you, right? There's heaps and there's clustered tables. Somebody came up to me in this very aggravated voice and said, You said that clustered tables are more efficient than heaps. I had a clustered index, and I dropped it, and I went to a heap, and my heap performance was better. And then I realized there are actually 3 types of table structures in SQL Server. There's clustered tables that have a really bad clustered index. There's heap structures, which are better than a very bad clustered index choice. And then there are tables that have a clustered index that is more effective for the manipulation that you are performing. So the right clustered index is really important. It's not just any clustered index that makes it more efficient. It's the right clustered index. So let's talk about a clustered table. A table, if it's clustered, will physically be ordered by whatever the clustering key is. So kind of like what's happening there, your data set would be picked up, copied, and literally reordered. And if you had 20 rows per page, you'd end up having 1 through 20, 21 through 40, 41 through 60, all the way out to, let's say, the 80,000 rows that you had in that particular table. Assuming in this employee table that no one's ever left, no one's been fired, no new people have been hired, and all 80,000 people are still working there. So it's a little bit of a strange company, but we'll go with that. So we literally have all 80,000 records, and then what they do with this clustered structure is they create a doubly linked list. So we have a previous page pointer and a next page pointer on every page, essentially as another mechanism for traversing this data set. There's 2 mechanisms for traversing a B-tree structure or a clustered index, the IAMs or the doubly linked list. So now there's multiple ways of accessing this. But if you don't choose the right one, they might be horribly expensive to maintain. With the right types of indexes, often you can get better performance and maybe even reduce the amount of maintenance that has to be performed against those objects and tables. So when they're first created, they might be very expensive to create and build. So let's look what it looks like all the way up to the root. All I showed you on the last slide was the leaf level. They always build the leaf level first. So if I say I want a clustered index by employee ID, they take every data row and literally order it by employee ID. But that doesn't really help us. We need to have some form of way of seeking into this data set. So what they do is they take 1 entry for every page of that leaf level, and they put that into an intermediate structure. So if we had 1 through 20, 21 through 40, 41 through 60, then records 1, 21, 41, 61, 81, all of the first values from the pages, because all of the other values are ordered, will be essentially stored in the next level, meaning it's very scalable. And the narrower and smaller these indexes are, the more entries you can fit in a page, the narrower and smaller your tree structures are. Turns out, even though we have 4,000 pages, the number of pages we need in the intermediate level is only 5, because in this particular structure, all we're putting is the clustering index key and a pointer to which page it is. So it turns out we can fit lots of those on a page. So we scale up to a root of 1 page very quickly. Again, we only need 1 entry for every page of the level below. So we need this value, we need this value, we need this value. Well then, at this level, where there are only 5 pages, we need those 5 values. So it would be 1, right? 16,000, 32,000, 48,000, 64,000, right? And there's our 5 values, and here they are. So now, if you think of how many we can fit on a page there, it's unbelievable, because it turns out we can fit, I think it's 809 of those index entries per page. So our root page has 804 slots available. 804 slots, each of which represents 16,000 records. So what's 804 times 16,000? It's a pretty darn large number, okay? And the point is, this index structure will stay fairly stable until we hit whatever that number is. And then it's a very simple split with a new root, and that is going to last for a tremendous amount of time. So the point being is these are incredibly scalable and very stable, even as your data manipulates and modifies. So let's talk about what the non-clustered indexes look like. If the clustered index physically orders the data, and the non-clustered index helps us look into the data, then we have to get some insight into what these look like, because we can only order the data one way, right? So a non-clustered index is actually duplicated information, but not the entire data row, just the values that you want to put into this non-clustered index. And there will be some way of looking up the corresponding row. So remember I said that a non-clustered index is dependent on whether or not the table is clustered or not. So if you have a non-clustered index on a heap, then you're going to have something called a record locator, right, or a record ID. If you have a non-clustered index based on a clustered index, then you'll have the clustering key. And I'm going to show you what this looks like in just a moment. So I'm going to recommend a clustered table and put a non-clustered on that. The heap is generally not recommended for lots of other reasons. So I want to focus on the clustered table with a non-clustered. So the example that I like, if you create a unique constraint, you will automatically create unique indexes. And those unique indexes will include the column that is in the unique key, plus, if the table is clustered, the clustering key. Okay. They will then take that set of information and physically order it. That, since it's so narrow, won't take up very much space. But that will effectively become the leaf level of the non-clustered index. Then, just like we did for the clustered, we'll take the first value from every page and build that up till we get to a root of one page. Since the Social Security number and employee ID combo is only, well, let's say Social Security number is with dashes 11 bytes, and the employee ID is an int, that's 4 bytes, so it's 15 bytes, we can fit roughly, I think it's something like 539 of these on a page. Yeah, in fact, I put 539 there to remind me. So we can fit 539 of these on a page. So if we've got 80,000 records with 539 on each of the pages, it doesn't take that many pages to store this. So we have 149 pages. We take the first value from each of those pages, and we put that into the root, and we're already at a root because we could fit roughly 539 records on the page. It turns out it's not quite 539 for this one because that pointer is 6 bytes. So they can only fit something like 477, but still way more than what we need. So we're right at a root. Very small tree structure. So now we start thinking, okay, how is this used? Right? How does SQL Server use this? And how much does this cost us to have this? So the first thing that I want to stress, though, is the relationship that we just created. We've got a clustered index and we've got a non-clustered index. And that non-clustered index includes the clustering key in the non-clustered index. That means, well, think about it. You're in the back of a book, and it tells you that the information you're looking is on a particular page for that particular data set, for that particular row. What does that actually imply? Uniqueness, if you think about it. We go to the index, and we need to find where that information is represented in the data set. Have you ever been told that your clustered index needs to be unique? SQL Server doesn't require that at all. But if you don't create a clustered index on something which is unique, SQL Server will have to, I love this word, uniquify it. Right? They will have to go through a process of uniquification where they will take that row, if you put a clustered index on name. First one goes in as Jones. Jones is unique. The second one goes in as Jones. That's not unique. They will put a 4-byte integer with all of the duplicated values, making the rows wider and putting information in that's not overly useful to your queries. You can't even see this information. It's just internally used. And then when they do the lookup from the non-clustereds into the clustered for that particular row, Jones 497, right, then the non-clustered index is slightly wider as well to have this uniquifier. So now on an insert, they have to check to see if the row is duplicated. They have to add the uniquifier, right? They have to store the uniquifier in the non-clustered indexes, right? And that takes space and overhead. So that is something to consider. If your clustering key is already unique, then you don't have this process at all. So the clustering key should be unique. Okay? So our non-clustered index not only includes the non-clustered, but the clustered, which means that the wider the clustering key, the wider the non-clustereds, which can end up wasting space. So we want to make our clustering key as narrow as possible to help effectively look up those data rows, quickly and effectively look up those data rows with as little information as possible. So we want something which is unique and narrow, and if you have 25, 30 non-clustered indexes on a table, that means the clustering key is in 25 places. So you've got it in the data set and now in 25 non-clustered indexes. So if that data changes, we have to go to 26 different places to modify that data. So we absolutely want the clustering key to be unique, narrow, and static. All right? So we start thinking about unique, narrow, and static, and something probably comes to mind. It might be the primary key. Might not. It might actually be something like an identity column. That is definitely unique, narrow, and static. But that usually immediately, for most people, brings this, but that creates a hotspot. I don't want that. I don't want some type of key which is ever increasing, because that means that end of the table is extremely hot. I'm going to tell you that in most cases, that's actually beneficial. An identity column, which is naturally unique, naturally narrow, and naturally static, has a benefit in that it is an ever-increasing key for performance purposes. The reason why everybody gets nervous about hotspots is that we all have, in many cases, a background, or at least we knew, that SQL Server used to do page-level locking. And if you had multiple people that wanted to access the same page at the same time, and we had page-level locking, then you would serialize all of your inserts. Everybody would end up waiting on that last page. But instead, if you have a page that can support multiple inserts at the same time, and then you start isolating some of your activity, the number of pages you need is reduced, and the pages you need will already be in cache. Might be counterintuitive, but when you really think about it, it becomes a benefit to have a hotspot for inserts, because you use less pages, the pages you need will already be in cache, and you get better insert performance as a result, because we do true row-level lock-in. So I did make one point at the very bottom of the slide. I just wanted to mention this. If some of you are doing what's called table partitioning, either with partitioned views or partitioned tables in SQL 2005, or have a desire, you may end up wanting to create a clustered index that is actually a composite key, which kind of negates my really narrow theory. But date and an identity is relatively narrow. Okay? And it's usually static, right? And it usually doesn't change, right? So it's static, narrow, and date identity. Since identity is very likely to be unique, date identity would be unique. And that can be an ideal choice to have large data sets where you basically have January and its ever-increasing keys, February and its ever-increasing keys, March and its ever-increasing keys. So there's lots of benefits to that. So that's an okay comment. I get that question all the time. What about date identity? And I always laugh. I'm waiting for the question that I'm sure some of you are thinking, what about a GUID? Right? How many of you are thinking that? Okay, quite a few. That's kind of what I always end up getting. So let me give a second here on why the identity is good, and then I'll make a couple of points on GUIDs. But clustering on an identity, it's naturally unique, naturally static, naturally narrow, and it naturally creates a hotspot. There is a point in some cases, usually on the higher end, where you're hitting 400, 500 inserts a second for a given table, that you might end up having some delay in doing this. I wouldn't go to a totally random index structure at that point, or try to randomize the inserts. I would try to create, let's say, 2 hotspots or 3 hotspots. So you have ever increasing in one area, ever increasing in another. You might create a composite clustering key on something like country and ID. And if you deal with, let's say, 3 countries, then you'll end up having 3 hotspots. That's a really good choice if you have a large amount of data going in, more than 400 inserts a second in a bigger table. But most of you, I would guess that not everyone in this room falls into the 400, 500 inserts a second for one table. But if you do, that's a little bit more work to strategize for. But the general, the norm, this is fine to cluster on an identity column. So this is probably a good point to make as well. I would recommend clustering on something which is unique, narrow, and static. But to kind of pull back on those concepts, there are really 3 types of tables, right? The bad clustered index choice, the good clustered index choice, and the heap structure. And I just put together 3 slides to kind of summarize this before we move on to traversal. So a poor clustered choice, and why, is that last name concept. Because all the inserts are going throughout the table. And some people say, yeah, but that seems to fairly well balance and distribute the IOs and distribute that activity. Yes, but if all of those pages are, let's say, full, because by default when indexes are created or rebuilt, the default strategy is that they will fill all the pages to 100% capacity. So now if a new Jones comes in and the Jones page, or the page on which Jones resides, is full, they have to make room for it. Now don't worry, they're not going to shift everything down. That'd be horribly expensive. But they have to do something called a 50-50 split. They might take half the data and move it. So now we've got A's, B's, we get to some Jones, the rest of the Jones are over here, and then we come back. And we go all the way through the rest. Now, if that happens once or twice, it's not so bad. But the more that happens, the more fragmentation you have. So as soon as you start to have inserts, updates, and deletes, you'll probably have fragmentation. But fragmentation in the clustered structure, when it comes to certain types of rebuild strategies, it might actually require an impact to your availability. So I usually like to more proactively minimize the fragmentation in the clustering structure. So this one is one of the worst choices that you could create. And that is exactly what you have with a GUID. So let's talk about that for a second. A GUID, if you're using either the .NET frameworks to call the GUID, right, and create the GUID at the client side, or if you're using the new ID function on the back-end server, right, both of those create GUIDs that are effectively random, okay? There is a way to use a server-side call to generate sequential GUIDs. SQL 2000 doesn't have a built-in function for this, but SQL 2005 does. In SQL 2005, you can create a GUID column as your primary key column and then use a function called new sequential ID. And that new sequential ID will guarantee that your GUIDs are sequentially generated. And that will help keep your tables less fragmented. But if you are doing this at the client side, if it's not central, there's no way to make it sequential, right? So if it's client side, you can't really do that. You might want to keep your primary key to be a GUID, but not cluster on it. So that begs a really interesting question. The primary key is one thing, totally independent of this. The clustering key is what I'm focusing on, and I'm recommending an identity. But in fact, the identity doesn't have to be the clustered index either. Those are three separate concepts that could be on three separate columns. Ideally, when you have an identity column as your primary key and you cluster it, that's kind of the best choice where everything comes together. But if you absolutely require a GUID for your primary key, what you may want to do is create a non-clustered index for it and then arbitrarily add an identity column to your table just to cluster on it so that the base structure stays more optimal. I just recently was working with a customer, and I said, oh, why don't you check fragmentation for me? Again, something I'm going to talk about in the defrag session, but I said, why don't you check fragmentation for me? And they had something like 387,000 pages. And then they said, oh, and I have a number here, 387,000 extent switches. And I remember going, you have exactly the most perfectly fragmented table. You could not have a table that is more perfectly fragmented than this table. In other words, every single page had essentially had a split, and that table was, I forget the percentage number for contiguousness. It was something like 1 or 2%. It was unbelievably fragmented. And I said, what's your clustering key? What's your structure? And of course, the answer was a GUID. And I see that all the time, that GUIDs create some of the most abysmally fragmented tables that will create a larger table, waste space. It wastes space not just on scans, but also it wastes memory, right? It wastes space in backups. It wastes space. It's kind of a dominoing effect. So you need to be real careful with these clustered index structures. So a heap would be better than that, to be honest. You go ahead and you say, okay, forget it. I'm going to create a non-clustered for my primary key, and I'm going to have a heap structure. You're going to get better performance just by doing that, okay, in that particular case for sure. But what I would do is take that one step further and say, you know what? I want not a structure that is unordered, such that an insert would have to figure out where the insert should go based on deleted space, because that can get expensive, right? If you have deletes, right, then they have to know where to do the insert. That costs you a little bit. If your table has a defined location for inserts, and that location is, again, at the end, that will help your insert performance as well as minimize fragmentation due to inserts. So the right clustered index is generally one that has an ever-increasing key. So an identity column, or possibly add one just for clustering, a composite date identity combination, really, that for those tables that have that kind of a pattern, but The key things to look for: unique, narrow, and static. All right. Now, I mentioned a few tips at the bottom there. Find the right clustered index for your environment, and try to automate the process of checking to see if your tables have become fragmented, because that will also help improve performance if they do become fragmented. But this will significantly reduce that. So now, if you end up clustering on an identity, it is very rare that you would ever do range queries for that identity, right? It's very rare that you would ever do a range query for your identity column. You'd usually do ranges for like last name and maybe states and country combinations if you're doing some type of demographic analysis. So you've got all sorts of different types of data that you want to analyze. You want to do sum of sales by customer, sum of sales by product, right? You want to do aggregations, which are clearly range queries. So you start thinking about that and you say, but my clustered index is not useful. So how do I create the right types of structures to make those range queries faster? And the answer to that is non-clustered indexes. So you are going to heavily rely on non-clustered indexes for performance. And then a lot of people say, yeah, but non-clustered indexes are these separate structures. How can they give me a gain? How can they be a benefit? Well, think about that index on Social Security number and employee ID for a second. If a non-clustered index's leaf level has a value for every row, that means that every non-clustered index has one entry for every row. So if you really think of a non-clustered index, in fact, I always like to do this. If I go back to this slide, this one right here, and I took off the title to it, if I just showed you that structure, and you literally saw a bunch of pages with social employee ID, social employee ID, social employee ID, all laid out, you couldn't actually tell me that's a non-clustered index. That could be a clustered index created on Social Security number for a table that only has 2 columns. The way I think of this structure is as a mini clustered table of a subset of my data. I almost think of it like a vertically partitioned set of data. And if you start to look at that, if I have a query that just wants Social Security number and employee ID, a narrower query, then this data set could be used to answer that particular query. But it gets way more interesting than you think. You don't have to have a where clause on Social Security number to make this useful. So let me cruise back to where we were and talk about this concept of finding the right balance and coming up with the right indexes. Okay? I didn't want to duplicate some content that I've already done on the web, so I've got some links for you guys. If you don't want to become like an indexing guru or expert, which there's not a lot of need for that in every case. In most environments, there are some great tools that you should consider using to get better performance, but knowing how to use those tools appropriately is important. So I did some webcasts. Now, they were done about a year ago on SQL 2000, so they're not 2005, but the same general principles apply to the ITW for 2000, which has now been renamed and rewritten as the DTA, the Database Tuning Advisor. So in 2000, we had something called the Index Tuning Wizard, which really just tuned for indexes. Now we have the Database Tuning Advisor. I would strongly suggest, as a starting point, it's not going to solve every one of your problems, okay? But if you look at your tables and you really start with a minimal number of indexes, less is more, okay? Don't over-index. That's going to cause you grief. So you start with a minimal number of indexes. You create your clustered index. You add your primary key. You add your unique keys. And then I would recommend a step where you manually index your foreign keys. SQL Server has never created indexes on foreign keys automatically. I get that question a lot. When did they stop doing that? They never did. But it can be beneficial for join performance to manually index foreign keys. So those are the first few steps that I would do. Then I would consider capturing what we call a workload of your activity and run it through a tool that will help you do some of the most basic, and in SQL 2005 it actually is much better, even more complex database tuning, and give you advice even in the forms of scripts that you can run to implement in your test environments to see if that is really giving you a gain. So a really good idea, consider if you want, to look at the webcasts. One is called Indexing for Performance, Finding the Right Balance. And then I have a 2000 defrag session, which is, it's actually very different because all of the syntax, all of the implementation is very different in 2005. But if you need to do this for 2000, that can be really helpful. Okay? So these are really good in terms of concept and implementation for 2000. Now, there's also, since I always get this, but what if I don't use a lot of profiling? There's a webcast on Profiler and a white paper on ITW. So all of those you should consider taking a quick review on. Now, let's get back to non-clustered. These are the key to your success. Without a doubt, by far, you will get orders of magnitude gains in performance by not creating a whole bunch of indexes, but by assessing and prioritizing and then creating some covering indexes to help improve your performance. And I'm going to demo this. You don't have to cover everything. So the first thing that I really want to stress is that if the columns that your query requests are anywhere within an index, but all of the columns are somewhere in the index, then that index is said to cover your query, which means there's a smaller version of just the data that you need that can respond to your query. They might have to scan to get to that information, but they'd still end up scanning a much smaller structure than scanning the entire clustered structure, the table. So if your queries are narrow, this is more likely to happen. And if you're not, I always ask, does anyone out there do select star from an 8-table join? Although I don't want to know, really, if any of you do, because select star from an 8-table join is horrible. You want all of the columns from here, all of the columns from here. You're going to see any of the columns that are in those tables for the joins twice, right? Nobody does this. You want a couple of columns from here, a couple of columns from here, a couple of columns from here, maybe a few columns from this table, right? But out of those 8 tables, most of the requests are very narrow. The narrower the request, the more effective and easier it is to tune. So look at this example. I love this example. All right, so going back to that concept of the non-clustered index on Social Security number and employee ID. If I have these two queries, employee ID, Social Security number, right, from the employee where the Social Security number is between a range, well, that's a no-brainer, really, right? If I want just the employee with their Social Security number for a range, then literally within that index that has all of the social and employee ID pairs, the range starts here, ends here. We're going to do a partial scan. We actually say it's a seek with a partial scan of that data. Very effective. But look at the next one for a second. And remember that our clustered index is on employee ID. So if we think, in fact, you know what's kind of a little bit interesting? I'm always hesitant in drawing on this, but let me do a really crude drawing just to make this make sense. Remember our clustered index. Our clustered index had 4,000 pages, 80,000 rows with no gaps. So 1 through 10,000 for employee IDs, so less than 10,000, would be 1/8 of the table. So we would read till we got to about 1/8 of the way. So 1/8 of the 4,000 is going to mean that to do a scan, albeit partial, of the clustered index to access a query that is select employee ID social where the employee ID is less than 10,000 is going to cost us these 500 IOs. Yet our non-clustered index, which is ordered by Social Security number, so employee IDs less than 10,000, where are they, right? There's some here, there's some here, there's some here. They're all throughout this data set. But this data set, if you remember, is only 149 pages. We'd have to do a leaf scan and filter out those rows that don't match, but a leaf scan of 149 IOs is better than a partial scan with a seek of the clustered index for 500 IOs. So this is the case where they're going to use that non-clustered index in a way that you might not necessarily expect. If you cover some of your more important high priority types of queries, then others of the less important queries may use some of those wider indexes because they cover the less important queries. So instead of doing table scans, they end up doing index scans and still get better performance than if they even did a partial scan of the table. So now I want to prove this with, really, how do you get the best performance? And I'm going to kind of dangle the carrot here a little bit as well, because there's some great features that you can take advantage of that you don't always want to take advantage of. So there's pros and cons. But non-clustered indexes are really a narrower clustered index of a subset of columns. And they can be used for seeks or scans. So if you can create the right types of non-clustered indexes, it's almost as though you're creating little copies of your tables to more effectively tune those tables. So I don't want you to cover everything, right? I'm not recommending that in any way, shape, or form, but I do want you to prioritize and cover some of those. And ITW for 2000, DTA for 2005 will definitely help, okay? And this include concept should make more sense now. An include is a way for you to create a wider leaf level so that you're more likely to cover queries where the index key can only be 900 bytes or 16 columns. You can end up having a leaf level that's wider, and the B tree still stays efficient and narrow at that limitation, okay, or less. And I've got an example that's actually less. So let's talk about an aggregate, because I can give you degrees of improvement and show you how different types of indexes still give you benefits. So an aggregate. Right? Most of you do aggregates, group bys, and maybe many different dimensions that you want to group by. I want sum of sales by this, by this, by this. And with different types of indexes, you'll see increased gains. So I could take every single query as if it were in a sandbox and tune the heck out of it. I mean, there's no doubt about that. I can definitely tune the heck out of a query. I don't want you to do that. Take the higher priority ones, tune those, and then see what else you really still need to tune. So again, your base indexes, go to DTA, and then prioritize and maybe hit some of these manual strategies. So aggregations is a great example. There's two types of aggregations internally in SQL Server. There's something called hash aggregates and stream aggregates. Imagine having all of your customer sales spread all over your desk, which is kind of like a picture of my desk. Not very organized. So if I have to do the sum of sales by customer, it's a little bit painful for me to go and grab that information to calculate out those sums. Now, if I were incredibly organized and I had every customer, right, ordered, and I had all of customer number 1, all of customer number 2, all of customer number 3, I could literally sum and get those values out. That's a stream aggregate. And prior to SQL 7.0, SQL Server used to order your data to do a stream aggregate, which, if it's a really large data set, ordering can be quite expensive. So now they have something that does an out-of-order aggregate by building a work table, right? So that's better, but if they can stream naturally from an index that already exists, they'll get better performance. So what I've done, okay, I have a script called indexing for aggregates. It goes against a database called Credit, which is on my website. You can end up downloading this. It's a 48 meg zip that expands to like 180 meg backup, which then restores to about an 800 meg database with a lot of free space for all the index stuff that you're going to end up doing. So the way that I'm going to end up seeing what's going on, two of my favorite things to do is I'm going to turn on statistics.io, which tells me the cost of a particular query in terms of the number of times they hit pages, and then I am going to turn on show plan. So here's that query, a fairly narrow, straightforward, yet very common type of query to take the member number, the sum of sales from the charge table. My charge table has 1.6 million rows. I'm going to group by member, and very likely that you probably want this data ordered by member. I'm going to add that on because that's a very common request. So I run this particular query. Again, I've got 1.6 million rows. I did reboot my machine, so nothing's in cache. So this first run is definitely going to take a few seconds. Took 8, not too bad. But there is the data. And at the end of the execution, right, I can see the IOs. It did 9,335 IOs against my charge table. And, oh, look, it created a work table. You don't really see any of the costs of the work table here. But over in the execution plan, you can end up seeing that we did a scan of the data, right? Then we built a work table, and you can actually see that it's the work table right in here. It's a little bit hard to show, but right in there it says, use a row from an input to build a hash table. The hash table is the work table, and then they have to sort. Okay, so it costs me 9,335 IOs, and it cost me a temp table. Oh, okay. If I had an index that instead of having to scan the table would allow me to scan a narrower structure, I could at least save on that 9,335 IOs. So this isn't the most ideal index, but if you were covering some other type of query and ended up having charge amount and member number somewhere in an index, that still would be narrower than doing the table scan, so we could end up scanning the index instead. So they built the index, and if I run this query again with no hints or anything, then we're going to see a very similar plan, but not a table scan and not so many IOs. So we look over at our messages, it's less than half of the IOs, but the execution plan is still a scan, then a temp table, then a sort. Okay, so the more users you end up having, the more expensive this can start to become. So here's another index where it literally orders the data by the aggregate. The first column is the aggregate. Then the second column is the data being aggregated. That means that I have all the members and their charge amounts ordered. So I can now do a stream aggregate. So I'll create that index, and a good point to make is that the orders of the charge amounts are irrelevant. That's not important in terms of aggregating. So really, this is an ideal candidate to use in the include. The only thing I really need to order are the member numbers, so I can just add the charge amount to the leaf level, and I can end up helping keep the non-leaf structure, the tree structure, even narrower by moving the charge amount to the include. So I'm going to end up creating both of these just for interest's sake. It turns out, oh, and you're going to love this. Remember how I said that SQL Server likes to use covering? Well, I have an index right here that's charge amount member number. I'm now creating an index here that's member number charge amount. So look what they do to build the index. They read the other index to build this index. They use covering anywhere they can. Anywhere that data set exists, they will use it to cover your particular query. Now these two are created. So if I want to run the query, I can force one with the covering index and force one with this covering with include. These aren't going to make that big of a difference between the two, but I'll run both of these. In fact, they'll probably equate to 50-50. But if I look at the IOs, okay, 4 less IOs out of 4,000. Ooh, right? That's not something that anyone would notice. In this particular case, it's not going to make a big difference. What do our percentages say? 50-50. Okay? So 50-50 in terms of the cost. But here's where it's really interesting. I'm going to take another script that I have, which is called a summary script, and I am going to take 3 executions. So now let's look at this for a second. I'm adding in a hint that says with index of 0. So let's look at this one just for a second. I say, don't use any index whatsoever. Do a table scan. So this is going to be a scan of the table with an out-of-order hash aggregate that's going to have to create a temp table. So that was the first scenario we looked at. The second scenario that we looked at was to use a covering index, but it still had to do a hash aggregate, so it had to build the temp table. And the third example is to use a covering index that allows a stream aggregate. And this is where you can start to see the more impressive differences between these different algorithms by comparing them against each other. So I run this, and I'm now running it all 3 ways. Give it a few seconds to complete with all 3 of these. I go to the messages window, and that first one with a work table, 9335. The second one with a work table, 3770. The third one, no work table. So what does that equate to in terms of my numbers here? 48%, 36%, and 16. That is effectively implying that this is, well, 300% faster than this one, and more than double faster, or twice as fast as this one. Okay, so I'm seeing some pretty good gains here. So now, this is a little bit maybe not nice, but there is yet another thing that you can do. Now, I'm not telling you quite yet what it is, but I'm going to go back to the summary. And remember, I just ran this 3 times. I'm going to add in another one at the very end with no hints whatsoever. Okay? So I'm actually going to run it now 4 times. So the first 3, we already know what it's going to happen, right? So it runs it, it gets the information. I don't know about you guys, but that fourth one seems a little bit better. In fact, it's kind of funny. They have a decimal rounding error here in this. It's something like 0.19, but since it doesn't even register 0.5%, it actually rounds down to 0. And that is literally 100 times faster than the best choice we had before. Let me tell you what's in the slides. I put the aggregate query, and I wanted you to be able to see all of this, so I actually put in every slide that represents what is happening through this set. So the table scan plus the hash aggregate, we saw the IOs, we saw the plan, right? An index scan with a hash aggregate, we saw the IOs, we saw the scan, right? And that was faster, right? Then we had an index scan with a stream aggregate, even better. And when we compared all three of them, we saw the numbers 48, 36, and 16. Everything looks good, okay? So what I just did is I avoided some of the concerns that we have with those three algorithms that we just saw. The more users there are, if there's temp tables being created, so in the work table examples, the slower and slower it gets. The more contention you have, the larger the temp DB is that you're going to need. Then your performance is actually going to vary execution to execution. So you have a lot of concerns with this. Now, what I just did to make the query 100 times faster is not something all of you want to implement, right? There's always a series of trade-offs. But what I implemented is another more interesting way of covering a query. And now, instead of just covering member number and the charge, I actually covered the member number and the sum. So I took that aggregated data set and stored it. I didn't show you this, but look at the IOs. It only did 35 IOs because it was able to go to a pre-aggregated data set to actually read this information. So this is called an indexed view. Okay? The gains are phenomenal, but there is a trade-off. So I don't want just everybody to go out and create a ton of indexed views. But in a database that's read-only, this is your new favorite feature if you didn't already know it. Indexed views are by far one of the fastest choices for large, complex, especially aggregations. There's other uses, and there's some really good white papers on indexed views. I'm going to point you to those at the very end as well. But indexed views are yet another special, more interesting way of covering because it allows you to cover more than just the columns, allows you to cover computations, aggregations, and effectively materialize a data set as defined by a view. So that's what an indexed view is. It's essentially a view of the data that you put an index on. They end up building the structure with the data in it. But just like any other index, as the data changes, they have to update it. So that means that depending on what you aggregate, you could end up creating some blocking. So you have to be careful with your choices. And this kind of brings this all together here. I recommend index views for aggregates if your aggregates don't create incredibly hot rows. Meaning, if you aggregate by something like member number, it's not that likely that you're going to end up having hundreds of rows coming in for a member number at the same time. But if you aggregate down by state, you'll effectively serialize all of your inserts by state. If it's a volatile database, you want to err on the side of fewer indexed views. If it's a static database or a read-only database, then you'll want to have lots of these because especially in an aggregate, they don't even take up much space because it's just the aggregated set. So, incredibly efficient and effective. So what's my point? My point is that you want to start with your base structures. You want to consider the right clustering key. You want to add appropriate non-clustered indexes. You want to consider various levels of covering, different types of covering. Covering for scans and hash aggregates isn't bad if the query's not critical, not run very frequently. But if it's run very frequently and there's a lot of modifications, I might create an index that's appropriate for stream, not an indexed view. But if I then take it one step further and I say, no, it's mostly read-only, I may go to creating an index on an indexed view. So I have levels of choice and improvement that I can make. I take the most important, highest priority, if it fits into the right category, and I create the most effective indexes. And often, things that aren't as critical, maybe we'll get the scans instead of the seeks. And you'll often get a much better balance of performance. And your include option is allowing you now more useful covering indexes. So finding the right balance, determine your usage, create your constraints, add your indexes to your foreign keys, capture a workload, run it through Index Tuning Wizard, DTA, depending on version, add your indexes to help improve your search arguments, your joins, and your aggregates, and unfortunately, you're not done. But I am, because it's our next session, and that's defrag. You have to keep your performance optimal by defragging that data. If it becomes fragmented, it will become less and less effective over time. So that's it for me. I hope you guys enjoyed this. I think you have some really good strategies, and I promise with the right types of strategies, with fewer indexes, you will get, in many cases, better balanced performance, and in some cases, orders of magnitude gains. So thanks a lot.